This video is going to cover pH curves and indicators of the topic of acids and bases. In the syllabus, you need to be able to interpret and sketch the shapes of acid-base titration pH curves for strong and weak acids and bases. And you should also be able to use these curves to work out which is the suitable indicator for a given set of acids and alkalis in a titration. The very last bit is really about enthalpy calculations, which is not directly related to the first two. These two are linked. So first of all, we're going to look at the shape of different pH curves for different combinations of acids and alkalis, or different types of acids and alkalis. And then we're going to look at how we use those pH curves to help us choose suitable indicators for different titrations, as you would need different types of indicators for different types of titrations. So this next bit, you don't need to necessarily explain in the exam, but it helps you understand why the pH curve is not linear as you add an acid to an alkali, or when you add an alkali to an acid. So here we've got an example where we've got hydrochloric acid added to sodium hydroxide, and the stoichiometry is 1:1. So when we add the alkaline to the acid, the pH is going to start off quite low because we start off with just the acid with no alkaline. And then as we add the alkaline, the pH will increase. But the increase won't be linear because of the nature of pH being on a log scale, or being worked out using log to the base 10. So just remind ourselves that pH 1 is when the concentration of H plus ions is 0.1 moles per decimeter cube, and pH 2 is 0.01, pH 3 is 0.001, and so on. If I were to add alkaline and the pH goes up from 1 to 2, well, that's a difference of 0.09 moles per decimeter cube in concentration of H plus ions. But going from 2 to 3, that's a smaller difference, and going from 3 to 4 is an even smaller difference. So these jumps in pHs are not in equal steps. So let's say I start off with just the acid and the pH is 1, and I add this amount of the alkaline to get to pH of 2, and then I add a small amount of alkaline to get to pH 3, because the step from pH 2 to 3 is smaller. So I get the smallest increase from compared to that volume. This is a smaller volume, so I'm going to get an increased pH 3 with that volume, and I have a smaller volume than this for the next step. Let's say I get to there to get to pH 4, and so you can see this is not a linear increase. It increases and steeper and steeper. So I don't think you would need to explain the shape of this curve, but it's nice to understand why it's not a straight line. So what we need to do is look at the shape of different pH curves for different types of acids and alkalis. So for a strong acid versus strong alkali or strong base, we get this sort of shape. So if we were adding an alkaline to an acid, it would increase from low pH, and then we get this sudden jump in pH values, and then it will taper off. So this is why we need to add drop by drop near the endpoints of the indicator when we do titrations, because a small increase near the endpoints means a big change in pH. So if you add too much alkaline, you go past the equivalence point. So if we add acid to an alkali, we start with a pH which is high, and then we end up to a low pH. So the curve will look like this instead. So what we're going to look at next is the difference between the equivalence points in the titration and something called the neutral points, which is slightly different, and also the end points of an indicator. And it's really useful to know the differences between those three things. So the equivalence point is the point in the titration where the moles of the acid and alkali are in their correct proportions in terms of the stoichiometry in the equation for neutralization. So if I have a monoprotic acid and a monobasic base, we have a stoichiometry 1:1. The moles of the acid and the alkaline should be the same at the equivalence points for these types of neutralization reactions, or these type of titrations. If I have a diprotic acid and a monobasic base, then the moles of the base will be twice as many as the moles of the acid at the equivalence point. So the equivalence point doesn't mean they're the same number of moles of the acid and alkali. It just means that they are in the correct proportions in terms of their stoichiometry at that point in the titration. So for strong acid and strong base at 25 degrees C, the equivalence point is at pH 7. So it's in the middle of this vertical part or vertical section of the pH curve. For strong acids and strong bases, the equivalence point is the same as the neutral point. The neutral point is the point in the titration where we have the pH to be 7 at 25 degrees C. You could have a titration where the equivalence point is not at the neutral point, where the pH isn't 7. So to illustrate the point that the neutral point is not the same as the equivalence point, if we have ammonia reacting with hydrochloric acid and we have equal moles of these, so that's the equivalence point, I've added the same moles of the ammonia to acid, I'm going to get ammonium chloride, but the ammonium chloride produced is going to be a weak acid because it can form hydroxonium ions in water. So the pH at equivalence point will be below 7. It won't be neutral, so it won't be a neutral point. So the equivalence point for ammonia with hydrochloric acid is going to be below 7, and it won't be the neutral point because the pH isn't 7 at 25 degrees C, which is neutral. So another example is with a strong base and a weak acid like ethanoic acid. When we react these together, we're going to get the sodium ethanoate here. So in this case, the ethanoate ion is acting as a base because it can react with water to form its conjugate acid, the ethanoic acid, and hydroxide ions. So in this case then, the equivalence point is going to be above pH 7, so it's not neutral. So again, we can have an equivalence point where we got the right amount of acid and alkaline to react in the correct proportions according to their stoichiometry, but the pH at that point is not pH 7 because we have in this case a alkaline being produced as the product. So the last definition we're going to look at for now is going to be the endpoint, and that relates to the pH at which an indicator changes colour. And different indicators have different endpoints, so they change colour at different pH ranges, and we look at more detail when we look at indicators. Before we look at indicators and how to choose a suitable indicator for a particular titration, we need to look at pH curves. We already see the pH curves for strong acids and strong bases, where we got a very low pH at the start for the strong acid, ending up to a very high pH for a strong base, and the middle of the first core section of the pH curve is at 7 for 25 degrees C. For a strong acid and a weak base like hydrochloric acid and ammonia, the pH curve is going to look something like this if we add an alkaline to the acid. If we add an acid to the alkaline, it would be this shape, the opposite way round. But in both cases, the highest pH is going to be below, way below 13, because the alkaline is not a strong base. The base is not a strong base. So unless it's very, very, very concentrated, we're not going to likely to have a pH to be very high at the end here if we're adding the alkaline to the acid. Hopefully you notice that the middle of the first core section of the pH curve is below 7, as we mentioned before. So for a strong acid and a weak base, the middle of the first core section of the pH curve is going to be below 7. So for a weak acid and a strong base like ethanoic acid and sodium hydroxide we saw earlier, the pH curve, assuming that we're going to add alkaline to the acid, will look like this. We start off with a pH which is further up, and we're going to end up with a pH closer to 13 than the one with the strong acid and weak base. And you notice that the first core section of the pH curve, or the middle of the first core section of the pH curve, is now above 7, and we explained that earlier in the video. By the way, this 25 here is the titer volume, and it depends on the concentration of the acid and the base, so it's not always fixed at 25. I've just happened to use that number as the titer volume. So from a pH curve, you can actually read the titer volume by looking at where the vertical section of the pH curve is. So lastly, here's the pH curve for a weak acid and a weak base, and this is rarely useful to us, as we see when we look at how to choose indicators, but you don't get a clear vertical section of the pH curve at all, so you can't see a clear equivalence point at all. So now we know the shapes of pH curves for different acid-base titrations. We're going to look at indicators and how indicators work and how to use pH curves to choose suitable indicators for different titrations, as not all indicators are suitable for all titrations. So indicators are coloured organic compounds that are weak acids and they ionize partially to give the conjugate base, and the colour of the undissociated indicator is different to the colour of the conjugate base. So the combination of the two colours is what we see as we use the indicator. So I've used this symbol to indicate the unionized indicator, and I've used this symbol as the conjugate base of the indicator. So methyl orange indicator, when it's undissociated, is actually red in colour, but when it fully dissociates, it forms a yellow conjugate base. So in acidic solution, this indicator equilibrium will shift far to the left hand side, and we see the red colour of methyl orange as the colour in the acid. If we have the indicator in a strong base, then the equilibrium will shift far to the right hand side, and we don't have much of the undissociated indicator, and we have a lot more of the conjugate base. So we see methyl orange as being yellow in an alkali. So the equivalence point for methyl orange is the point at which the indicator switches from red to yellow via the mid colour, which is the mixture of the two, which is orange. That gives the name of the indicator methyl orange. So at the end point, the concentration of the undissociated indicator and the concentration of the conjugate base will be equal. So we see an equal amount of red and yellow, and we get the appearance of orange. The pH at which methyl orange indicator changes colour, or the end point, isn't at pH 7. It's somewhere between 3.1 and 4.4, so it's around 3.7. So you can't use this indicator for all titrations. And I'll show you this when we look at the pH curves. Before we do that, I'm going to show you a different indicator, and this is phenolphthalein, and the endpoints for phenolphthalein, i.e. the pH at which it switches colour from the pink to the colourless or vice versa, is somewhere around 9.2, 9.3. And like with methyl orange, it only suits certain titrations, and we look at that when we look at the pH curves with these pH indicator ranges on them. Before we do that, just a quick note that the endpoint colour for phenolphthalein is pale pink. So now we're going to look at some pH curves and see how we can use these pH curves to choose a suitable indicator for different situations. So here we got the pH curve for a strong acid and a strong base, and I overlaid on top of it the pH range of these two indicators we looked at earlier. So I'm going to show you first that methyl orange is a suitable indicator for this titration. So this line here is the point at which the methyl orange changes colour from red to yellow or vice versa. That's the point where the indicator is orange. So anything below this point is going to be red, anything above that point is going to be yellow. So if we follow this titration curve at the start, the methyl orange is red, and it's red and it's red until it gets to this point where it switches to orange. So that's when you will see the indicator change colour, and it matches the vertical section of the pH curve. So it's in the right volume, will give us the right volume for the titration. So using methyl orange will give us the correct volume for this titration because it's the same as that at the equivalence point. Phenolphthalein is also a suitable indicator for this titration because here's the pH at which the phenolphthalein changes colour. That's the end points of the indicator, and anything below that pH, the phenolphthalein is colourless, and anything above that is pink. So the end point of the indicator at this pH here is pale pink. So if we follow the titration, the phenolphthalein is colourless until we get to this point where it suddenly changes to pale pink, and this is the volume we will read during the titration, and it matches the volume at the equivalence point. So the indicator will give us the correct volume to read for the equivalence point. So this would be a suitable indicator to use for this titration. So here we have a pH curve for a strong acid and a weak base. So we start off with a very low pH, and we're adding the alkaline to this, and the pH increases, but it doesn't increase to a very high pH because it's a weak base. So we can show you that in this case only methyl orange will be a suitable indicator and phenolphthalein wouldn't be. So if we follow the titration and look at methyl orange, we can see that as the pH increases, it goes from red all the way through until this point here where it switches to orange, and the volume we'll read there when it switches to orange is actually the same volume as that of the equivalence point. So this pH range of the indicator fits within the vertical section of the pH curve, and that's when we know it's a suitable indicator. So here we look at the phenolphthalein pH indicator range, and this range doesn't fit within the vertical section of the pH curve. So this won't be a suitable indicator, and we can see why. So if we follow the pH titration and we look at the phenolphthalein, we have colours all the way through here, and it only switches colour at this point here. And at this point, we are not reading the same volume as that on the equivalence point. The reading we'll get at this pH here will be much higher, or will be higher than the equivalence point. So we're going to get a wrong reading for this titration if we use phenolphthalein. So it's not suitable for this titration. So here's another pH curve, this time with a weak acid and a strong base. So we start off with the weak acid and we add in an alkali to it. And right at the beginning, once we start adding the alkali, the methyl orange would switch colour at this point. This is the pH here at which the methyl orange has its endpoint. So the volume we'll read would be here, which is way off compared to where it should be for the equivalence point. So the equivalence point is here, so we should read this volume. So this indicator is not suitable for this pH curve, and we can see that because the range of the indicator does not fit within the vertical section of the pH curve, whereas phenolphthalein has a range that fits within the vertical section of the pH curve, so would be suitable as an indicator for this titration. So for phenolphthalein, as we proceed with the titration, the colour of phenolphthalein is colourless all the way through here until it reaches this point, and this is the end point of the phenolphthalein, and that's where it changes to pale pink from colourless. So that's when we read the burette in the titration, and it gives me the correct volume for the equivalence point, which is here. Finally, we look at the pH curve for the weak acid and weak base titration, and here's the curve. And in this case, there's no indicator that is suitable, so none of these two indicators have the pH range or the indicator range within the vertical section of the pH curve, because simply there is no vertical section, so we can't use a suitable indicator to work out where the equivalence point would be in the titration at all. So now we've covered how to interpret and sketch the shapes of pH curves for different acid-base combinations, whether it's a strong acid with a strong base or whether it's a strong acid with a weak base and so on. So we covered this part of the syllabus. We also looked at how to choose a suitable indicator by looking at the pH curve for the titration and whether the range of the indicator fits within the vertical section of that pH curve. I'm going to leave this last section on enthalpy change of neutralization for a short video next.